Welcome back. Today we will talking about correlation analysis in Microsoft Excel. So let's consider. We have a problem. The relationship between a nurse's assessment and physician's assessment was studied. The following scores represent a nurse's assessment and a physician's assessment of the condition of 10 patients at time of admission to a trauma center. In general, we have a scope number and two variables. And there is a very convenient approach called correlation analysis. We can use it to estimate a similarity degree between two variables. To perform it, we can use very spreaded, very famous, so-called Pearson's correlation coefficient. We can calculate it, and this value can represent us a similarity degree between two variables, x and y. First variable and another variable. So first of all, we have to create a table exactly the same as described. We can run our Microsoft Excel and create exactly the same table as described. We can change width of column, appropriate column, by snap its border and drag it. We can select appropriate diapason and make it bold. Use Home, Font, Bold, or just press Ctrl B and center our content. And after that we have to insert numbers from 1 to 10 in this range. We can perform it manually, like this 1, 2, 3 and so on, and as usual we can use a question to perform it automatically. Pick up a previous number plus 1. It's some iteration techniques. And like this. It's very convenient way, because if we have huge amount of records, it's more preferable than inserting it manually. And let's prettify our table. Useful note: if we want to insert a few lines into the same cell, few lines of text, we can press left Alt Enter like this and click Enter. We can center our content like this. Use alignment, vertical alignment center option. Let's prettify our table a little bit. But don't forget about, if Excel application recognized your numerical values as type of number, it should be aligned right. For example, it's very actual for values with decimal parts. For example, 4,4. It should be aligned right. It's correct. In another case, you have to use another comma separator, would separate integer part and quantity one. Replace it, try to replace to dot. In my case it's wrong. But if you have that situation, you have to back a cell type, automatically recognition of cell types. Right click, format cells, general, and click OK. And insert your values with correct comma separator. 4.4, 4,4, depending on your case. Let's prettify our table a little bit. Select all whole diapason, right click, format cells, and for example we can perform something like this. Let's check out border. We can change it, select this style and use this option, all inside. Select this style and use this option, outline, and click OK. And we can try to separate our headers. Select our headers range, right click, format cells, and use this style, outline. Click OK. And we can use, for example, some filling techniques. Make it a little bit less bright, like this. Use some value of gray, and we can separate each of our variables. Select all table, right click, format cells, border, and use this line style just for vertical separators, and click OK. Good job. Next move. Okay, we have already performed table styling. After that we can visualize our variables x and y to visually estimate a relationship between two variables. Okay, let's insert some chart. Navigate to insert, and in the section of chart use this option, drop down menu, and for example this one, scatter with straight lines and marker. Make decision and ground your decision. You can use any of these, depend on your preparation. I can use scatter with straight lines and markers. Snap this and drag into a more convenient place. We can resize it like this. After that we have to specify our data ranges. Right click and select data. Remove all records if you have some. After that add new one. So we have to specify a series name. Let's pick up it. Let's create an line series plot for x variable. Pick up our header for x variable. After that we have to pick up, we have to specify and values along all x axis. This value, all x axis, we have this range from 1 to 10. After that we have to specify values along all y axis. Delete all this and pick up appropriate all y values like this, and click OK to apply. After that we have to add a series for another variable y. The same, pick up this, delete this and pick up this. And click OK to apply and click OK. As we can see, the shape for each data variable very similar. So we can expect a positive correlation. Let's check out it. Next move. Let's calculate an appropriate criteria and let's check an distribution type of each variable we have. So let's calculate skewness and kurtosis. As you remember, we have a very useful table. You can make screenshot. We can calculate skewness and kurtosis using appropriate built-in formulas. And we have critical values for skewness and kurtosis respectively. For alpha value of 0.05. So let's calculate skewness. We can insert one column left. Right click, insert, and calculate skewness using built-in formula. As you remember, each equation in Excel should be started from equal sign. After that, we can append a name of appropriate built-in formula. Each formula have a syntax with the brackets appended, and each formula requires some input variables, some input arguments. So we can specify appropriate numerical range for x variable, and we can propagate it right like this. Snap bottom right corner, drag and drop. As we can see, this counter will be increased automatically if we drag it. The same for kurtosis. So let's consider. We can compare our critical values and make decision about normality distribution according to this criteria for appropriate variable. For example, if requirements satisfied, we can fill our cell by green and by red if not. So let's compare. We have this value calculated, and for 10 records, up to 10 for skewness. If our data is lower than critical value, we can consider, according to this criteria, this variable have a normal distribution. Distribution is normal. And the same for y. Lower, normal distribution. According to this criteria for all y, for second variable. So let's compare critical values for up to 10 records with our calculated values. Minus 1.1 approximately. So, if calculated value below diapason, we can consider a distribution for appropriate variable is normal. In another case, if it's a C diapason, distribution is abnormal. Distribution is normal for this, and in this case also. So at this point we can make decision. We in general for both variables we can apply most of statistical approaches because we have normally distributed data. But in another case, if at least one of these cells can be red, we can perform all next steps, but possibly it can be less representative. Okay. Move next. We can write our conclusion. For both variables, according to all parameters, skewness and kurtosis, we have a positive decision, and in general all our case is normally distributed. Next move, we have to correlate and Pearson's correlation coefficient. But before we perform it, let's talking about what is and Pearson's correlation coefficient. It's a very useful parameter we can calculate, and it's lay in a range from +1 to -1, and there are a few critical values. So if we have an Pearson's correlation coefficient +1, it's equal to +1, we can talking about total positive linear correlation. If we have an value approximately equal to 0, we can talking about a case with no correlation. There is no correlation between first variable and second one. And we have some mid cases. For example, if our value is +0.5, we can talking about just positive linear correlation. Between 0.5 +1, strong positive linear correlation. Between 0 and dot +1, between 0 and +0.5, we can talking about low positive linear correlation. And a mirror case. For value -1, total negative correlation. For 0, no linear correlation. For -0.5, negative correlation. For the range from 0 to -0.5, low negative linear correlation. For the range -0.5 to -1, not included, we can talking about strong negative linear correlation. Let's visualize few cases. For example, we have first variable A and second variable B. We can calculate correlation coefficient using built-in formula CORREL, and we can build a chart. As we can see, we have a case with exact matching. Two vector variables B and A are equal. We have a value of Pearson's correlation coefficient +1. It means total positive linear correlation. Both our variables are matched. A and B have exact matching. Another case. Why Pearson's correlation coefficient is so useful? Because it have some pros, some positive characteristics. It's invariant to the all y shifts. For example, we can calculate our b variable by adding any value to the variable a. In other words, we can shift our variable vertically one between other. It doesn't matter. In any case, in any shifts, in any vertical or y shifts, correlation coefficient always will be +1. And the same, there is another positive characteristics. Pearson's correlation coefficient is invariant to this all y scaling. We can calculate our variable b by multiplying variable a to any value. It's another pros for Pearson's variation coefficient. As you can see, total positive linear correlation is present. So let's illustrate another case. -1 total negative linear correlation is present. When it's happened? It's happened when we have situation like this. Our variables are flipped one between other along all x-axis. In another case, our second variable is calculated by flipping left-right variable a. Just flipped horizontally. Another case, all in one. We have a situation when our variables are flipped horizontally and our variable b calculated from variable a by multiplying and by adding some value. As you can see, it doesn't matter. Pearson's correlation coefficient is insensitive to the shifts and to the scalings. Another case. If at least one element of our data set is different, for example, first element of B is different than first element of A, like this, we have a situation with a positive correlation. Our variables very similar one to other. The same for flipped variable. If our variables are flipped one between other, but one element of each is different, like this first element is different, we have negative linear correlation. Our data almost similar and flipped horizontally. Another case. Variables are completely different. Two random variables. In this case, we have a value approximately equal to 0. In this case, we can talking about no linear correlation. But there is a cons for our Pearson's correlation coefficient. It's very sensitive to the circular data shifting. As you can see, our data is equal. Our data are equal, but shifting for one sample, one between other. Just one sample shifted. In this case, we can see very low correlation, almost no linear correlation. It's a leak of this approach. So, once more, we can see exactly the same data. This value is calculated from this. This value is calculated, and this value calculated at the same as this one. Total positive linear correlation. So we can see our data represented as the chart. So Pearson's correlation coefficient is invariant to all y shifts. As you can see, this value is calculated from this value like this, +1. And representation, graphical representation and theoretical representation. Another case, invariant to all y scalings. Each of these value calculated from appropriative value like this, multiply by 2 +1, total positive linear correlation. Another case, this variable calculated from this in this way to calculate inverse vectors normalized to 1 like this, flipped, all in one. As you can see, this value calculated from this value in this way, flip our normalized variables, multiply by 10 and -1, scaling, shifting, flipping, and the same. Just these elements are different. The same, just these elements are different. And as you can see, both variables, both elements of both variables calculated using built-in formula random between. And we can see a case where our variables are shifted. Okay, let's calculate correlation coefficient using built-in formula CORREL. Let's merge, because this value calculated for both variables, and insert a formula equal sign, CORREL, brackets, and respectively specify a first range. Use your system argument separator. Pay attention, please use your system argument separator. In my case it's semicolon. And specify another argument and click enter to apply. As we can see, this value is calculated. So make decision. As we can see, our data are very similar and a little bit shifted vertically. But as you remember, Pearson's correlation coefficient invariant to the vertical shifting. As you can see, this value represent us. We have strong positive linear correlation. Strong positive linear correlation. Next move. Let's calculate it automatically. Navigate to the Data Analysis ToolPak. If you have not installed it already, first navigate to the File, Options, Add-ins, Excel Add-ins, Go. Use this checkbox, Analysis ToolPak, and click OK to install. So navigate to the Data Analysis, and use this option, Correlation. Click OK, and make settings. Our data variables grouped vertically by columns. We wanna include labels, include our headers, and we want to output our results at the same worksheet. So let's pick up output range, for example here, and let's pick up our input range, labels included, like this, from C2 to D11, and click OK to apply. As you can see, we have variable names X and Y respectively along rows and along columns. It's so-called correlation matrix. It calculates all possible cases. For example, correlation between X and X, exact matching, +1. Correlation between Y and Y, exact matching, total correlation, +1. And correlation between X and Y, the same as performed by built-in formula, the same value, it should be the same. And this value, as you know, should be the same, but just for economy we can use just bottom left triangle of our matrix, correlation matrix, because our correlation matrix is symmetrical along main diagonal, and always correlation matrix have main diagonal filled by ones. And we can make some conclusion here. For example, there is strong positive linear correlation present. We can consider it looking at our scatter plot and keeping in mind calculated variables of Pearson's correlation coefficient automatically and using built-in formula. As you can see, in this case, nurses and physician assessment very similar one between us. We can make its conclusion. So thank you for your attention. See you next time. So welcome back, and let's perform another task. Task number 2, just for demonstration. As you know, Microsoft Excel application have a very useful feature. We can apply some regression techniques. What is regression? It's a technique for reducing our data dimension. In other words, we can simplify a representation of our data complexity. We can decrease our data complexity. Why we can use it? First of all, we can reduce memory requirements to store our data. We can estimate some trends, linear trends, and make some forecasts. We can use different approach to apply so-called interpolation and extrapolation techniques. For example, if we have some data and we have few samples along all x diapason, we can calculate some values between samples we have. And the same for extrapolation. We have calculate some extra samples we have not still. And the same, in another word, we can talking about forecasting. We can talking about forecasting of our process. So first step, we can create table exactly as described. Starting from 1 to 10. Prettify our table a little bit. Ctrl B, Ctrl B, right click, format cells, this style outline, this style inside. Like this. So it's completed. Let's create a chart. Let's create a chart. Navigate to Insert. Maybe we can use this scatter with smooth line and markers. Or this one. Let's use this one. Drag it and allocate it into your preferable place. And the same approach as previous. Right click, select data, remove all records if present, add another one. We have just one series. Series name is sales volume, all x variable, all x values, delete this and pick up all y values and click enter to apply and click OK. Next move, we can enable legend, for example, on bottom. Next move, We can add some trend lines to our chart. Linear, logarithmic, power, exponential, and polynomial respectively. So, linear. In another word, it's our linear trend. It can be positive or negative. Right click, add trend line. So, as we can see, our original data series have a color of blue. We can use another colors for another trend lines. So first of all, it should be linear. Scroll down a little bit. Use this option. Display equation on chart and display R² value on chart. And we can use forecast option of forecast. For example, we can calculate forecasts of 5 forward period. Like this. After that, we can change a default color. For example, it should be black. After that, we can allocate our equation in more convenient place and check out. We have an R² value. In another word, it's a coefficient of determination. If this coefficient of determination equal to 1, we have exact matching. Our regression model is absolute. As you can see, there is so-called coefficient of determination, and if we have scattered data and some regression model, we have calculate an accuracy of this model. In most general case, it can be expressed as like this. There is a most general definition according to this equation. In the best case, the modeled values exactly match the observed values, which result is 1, and R² value will be equal to 1 in the case of exact matching. If we have another case, a baseline model which always predict mean values of our scattered data, in this case we'll have R² value equal to 0. And models which have worse predictions than this baseline, worse, will have a negative R² value. It's an representation. So, as closed our R² value to the 1, as perfect our estimation accuracy of our regression model. Next move, let's insert logarithmic trend line. Select this, right click, add trend line. Logarithmic, the same, display equation R², and use 5 forward predictions. Like this. And change an color of curve. For example, red. and move our equation in more convenient place. As we can see, in our case, logarithmic regression is lower, have a lower accuracy than previous one. What about power? What about power? The same. Select our original series, right click, add trend line, power, display equation, display R-value, 5 periods forward, forecasting, and use a color, for example, yellow, and move our equation. Next move, use exponential regression technique. Left click, right click, add trend line, exponential. Forward 5 times. For example, it could be green. And last one, it's an most complex and in general most accurate regression techniques, polynomial. Let's perform it. Right click. And use polynomial. And we can use order at least 3. The same. And for example, blue. As we can see, it's very accurate. Very accurate. Almost matched our curve. So, next move. We have to calculate it manually. All this, and after that we can calculate it manually in forecasts included. At least 5 times. So let's perform it manually. Insert few rows and determine appropriate regression techniques winner, like this. And using this equation we can copy it, Ctrl+C to copy, escape, allocate cursor in this cell and insert appropriate equation. Remove all symbols left on equal sign and replace x variable by appropriate scope number. Multiply by this and click enter. And propagate its right, forecasts included. Oh, it should be multiply. Multiply, don't forget about multiply, forecasts included. So, very similar. We have a black variable, it's very similar. And the same for all other regression technique. Second one, logarithmic. Escape, allocate cursor here and insert equation. And the same, multiply by logarithm and pick up this scope number. Click enter to apply and propagate its right. And the same for another regression technique. For third one, power 1, 2, 3, number 3. One, two, three. Power. Like this. And for the technique number 4, 1, 2, 3, 4, exponential. One, two, three, four. 1, 2, 3, 4. Exponential. Like this. Exponenta multiply by this in the degree of this multiply by first scope. Enter to apply, propagate its right. And the same for the most complex technique, polynomial. And modify your equation like this. And click enter to apply and propagate its right. Don't forget to save. And as we can see, according to the R² value, most accurate regression technique is polynomial 1, because this value very close to the original one. And we can make decisions. Most accurate regression technique is polynomial. Thank you for your attention. See you next time.